Sometimes it's necessary to protect certain functional groups, and the first protecting group we're going to look at is the trimethylsilyl or TMS protecting group for alcohols. So let's say, for example, we have an organic substrate that has more than one functional group, right? Such as this one here. It has both an alkyl halide and an alcohol. And let's say we want to react the alkyl halide with conditions that would be incompatible with having an alcohol also present, because the alcohol, let's say, might interfere with the reaction that we're trying to perform on the alkyl halide. So in this case, we might want to what's called block or protect the alcohol from reacting. And so what that involves is temporarily removing the proton on the alcohol and replacing it with another group. In this case, we're going to convert the alcohol to a trimethylsilyl ether, and then we can perform the reaction on the alkyl halide that we want to do, and then later on we can remove the TMS group and convert it back to an alcohol. So just kind of go ROH. Right, so the idea of the blocking or protecting group is we can temporarily convert a functional group like an alcohol to something else that would be unreactive towards certain conditions, and then later on remove that blocking group to show us the alcohol again. Okay, so the conditions for protecting the alcohol with the TMS group are trimethylsilyl chloride and triethylamine. So that is abbreviated TMSCl and then ET3N. And that will produce again what we call our trimethylsilyl ether, which is unreactive towards basic conditions. Let's look at the mechanism for introducing the TMS group on an alcohol. So if we have our alcohol, right, just as a reminder, we can treat this with TMS chloride and triethylamine. Triethylamine is a non-nucleophilic amine base, kind of similar to pyridine. And the product will be our TMS ether. And the reverse reaction, so later on when we want to remove the TMS group, we can use one of two conditions. We can either use acid or we can use something called TBAF, which stands for tetrabutyl ammonium fluoride. Okay, so let's look at the mechanism for protection first. So we have our nucleophilic alcohol, and then if we draw in TMS chloride, again, silicon is larger than carbon, so we're able to do an SN2 reaction on what looks like a relatively hindered atom, but since it's silicon and not carbon, it's much larger. So there's room for backside attack. So if the alcohol attacks and chloride leaves, so we get an intermediate where the oxygen is positively charged. And that's what the triethylamine is there for. Again, it's our non-nucleophilic base used to prevent the formation of HCl. So we kicked out some chloride And without a better base, the only base available would be chloride, which would form HCl, which would not be ideal under these conditions. So our triethylamine can come in and deprotonate this to form the product. So this is the TMS ether, and it's often abbreviated with just writing OTMS. All right, so the removal, we'll look at the mechanism of the removal of the TMS group with tetrabutyl ammonium fluoride. So what does that look like? Basically it's an ionic compound where the nitrogen has 4 butyl groups and is positively charged, and there's fluoride as the anion counterpart. And the reason why this is used and not, let's say, sodium fluoride is because of the highly organic nature of the ammonium ion, which helps get the fluoride in solution. So it turns out that fluoride has a strong affinity, in other words, makes a strong bond with silicon. So if fluoride gets in solution, it will attack the silicon and kick out the alkoxide now as a leaving group. All right, let's try that again. And then there would need to be some kind of workup to protonate the resulting alkoxide. All right, so either a water or an acidic workup would convert the alkoxide back to the alcohol.